Hello, let's look at how the Bequant BQN or the Cambium QoE, which are the same product, can help in reducing excessive network latency in your network. Excessive network latency degrades the quality of experience of your users. It certainly has a really bad effect on online video games. It also can spoil voice over IP and teleconferences over Teams, Zoom, Google Meet. And beyond a certain network speed, let's say 50, 100 megabits per second in almost any home, really latency determines quality. So what's the origin of latency? Latency comes from queues in bottlenecks. Whenever there is any kind of speed limitation, whether it is because of congestion or because you are enforcing a rate plan, there is usually a queue where packets wait because packets are coming from internet from somewhere at a higher speed than what the bottleneck allows, and the packets accumulate in the queue, and they have to wait. Every time they get into the queue, they have to wait until the queue in line until the queue empties, and basically that waiting time is what causes latency. Now the queue can in many cases be overrun. There can be more packets maybe coming than the queue can hold, and then you will have packet losses. So Bequant provides the most advanced queuing technology in the market to avoid that excessive latency and losses in these situations. So let's look at this within a real environment, where we have on the right the internet. Here in this diagram we will place a Bequant node with all optimizations turned off. We're just going to see what is going on with this node in this setup. Then we will have an access gateway, in this case a microtip router with a 200 megabits per second rate limit. Then we will have a customer premises equipment, a Wi-Fi router, in this case with 600 megabits per second channel, so it's not the bottleneck. And then we will have a laptop. We have laptop, this laptop, which is connected via Wi-Fi with this Wi-Fi, a link to this Wi-Fi router running 5G AX channel, 80 megabits, 80 channel at this frequency with no interference, which can give us around 600 megabits per second channel. So then we'll have an access gateway with a 200 megabits per second rate limit, which we can see here. It's another it's a microtip router. We have this 200 megabits implemented with 300 packet P5 for queue. Okay, and we also have then a BQN node, in this case with all optimizations turned off. So, you can see here duration optimization, yeah, everything is off. We're just using it to see what is going on. And then we have the internet. we start testing with this setup. We go to this buffer bloat test from waveform, which is one of the most used for latency and buffer bloat measurements. And we are going to see this subscriber here in live mode on the BQN. So here starts the test. It first does some measurements without any load, very little load, less than 1 megabits per second, 7 milliseconds latency. And now it warms up, starts running at full speed, in this case 200 megabits per second, and it's not getting to 200, even though in reality it is getting to 200. The measurements are very variable with Wi-Fi always. Now it will do it uplink. See, first downlink, now uplink, and yeah, we will see. Okay, so these are the results. Almost done. Yep. Some people will say that maybe we can reduce the latency by just having queues with smaller queues, because then the fewer packets can have to wait in the queue. But that really doesn't work. Let's try it. Instead of using these 300 packets, let's try with 100 packets, and these numbers will depend on the speed. So for lower speeds you don't need as many packets, but you do need a minimum packets in the buffer, otherwise you'll see the problem, because now we'll have same setup, but instead of 300 packet buffers here, we'll have 100 packet buffers, queues in this place. Let's see what the difference is. Oops. So the problem we'll find will be the packet retransmissions, the losses we'll encounter with very shallow buffers with fewer packets than are required, because the queues will be overrun. And so while the unloaded latency is fine, we'll see that just as it is warming up, when it reaches high speeds, now see that packets losses will be very sustained at very high levels. The way to reduce latency is to use AQM, Active Queue Management. Instead of the first in, first out queues we've been using, these queues, which follow methods like cake or FQ Codel, what they do is that they measure the time that packet stays in the queue, and when packets stay too long, then they are dropped preemptively in a smart way. First, packets that came in first, not the last ones, and in that way, the nodes that are sending the traffic, either the content servers or internet, or the laptop when it's sending data uplink, they will see those packet drops and they will interpret that as having reached a limit, and then they will start sending at a lower rate. By getting both ends to send at a lower rate, closer to what the rate limit is, basically you avoid latency. So let's in our case use a cake queues in this MikroTik router. Cake is a little more advanced than FQCodel. FQCodel is more of a standard, and but Cake uses more CPU. There are different advantages to both. So let's get here and select and build a new queue type here. Let's say 200 megabits Cake. Yep. And here you select the speed directly here. Okay, let's use default values for all, and let's use that instead of what we had here. Okay, I think we no longer need to set these here because the speed will be set by the queue itself. So we now have this Cake queue with 200 megabits here set, and let's test this. Oops. Yep. We'll start looking at what goes on. Same unloaded latency, that's good. And see how we are reaching those 200 megs, but with almost no latency, basically. Increase. Same thing, uplink. So we get much better results. However, we do see that here you do see that the losses can be a bit high, but this is to be expected because that's the way that this works. Active queue management works by preemptively dropping packets. However, the end result is that we basically get much better buffer bloat latency results. So can show you now that you can do this much better with a Bequant box. We, instead of enforcing the rate limit with an access gateway, which could also be a presim box, which can also do these very advanced FFQ, CODEL queues, or Libre QoS, which will do Cake. We have our own improved FQ CODEL queuing, but we also have TCP optimization, and the combination of these two in our queuing model produces much better results. So let's show you. Let's now first get rid of the queues. Okay, in the access node, we'll just now transparently let things go through, and let's configure the Bequant node to apply those 200 megabits. We have a policy here. We'll select that for the IP address ranges to get 200 megabits. Okay, here, and we'll now activate all the optimizations which we had disabled. Okay, everything is okay. All right, and we now it. Yes, 200 megabits policy applied to it. And now we put this live mode and we test again. Okay. So okay, so it's now warming up and have this 200 megabits per second being forced. In downlink. And uplink. Okay, so we can see now that we've obtained these similar very good latency results, but with no retransmissions. This is no small improvement over FQCodel or Cake, because we are avoiding up to 5% packet losses, which can be significant. So far we've seen that to reduce latency while enforcing rate limits, you have to use active queue management, or even better, a Bequant box, which will avoid losses thanks to TCPO plus active queue management. Now, the problem doesn't end here. In fact, there's a very typical situation in which, in fact, you will not get much with normal ACM queuing, because here, for instance, what happens when it is actually the Wi-Fi channel that is limiting, when the traffic is being limited not by the rate plan, which in this case is 200 megabits per second, but by Wi-Fi going slower than that. So we'll see what happens. We'll turn off the optimizations in BQN. We'll just use it again just to see what is going on. And in this case, the problem is that all the AQM features are only applied when the traffic reaches the limit being enforced. If the traffic is not reaching that limit, then this is not being used at all. So what will dominate this situation will be the buffers, the queues in the 160 megabits per second Wi-Fi router. The Cake queues in the access gateway limiting at 200 megabits per second will do nothing, because packets will only be queued in the slowest node. To implement this scenario, we have changed the Wi-Fi router. Instead of using 80 megahertz channels, we have selected a maximum of 20 megahertz channel, which will limit the speed up to 160 megabits per second. And regarding the access gateway, we'll leave the Cake queues limiting at 200 megabits per second, even though they will do nothing, because packets will not be queued here, they will be queued in this slower Wi-Fi router. And in the Bequant node, we have made sure that we turn off all optimization settings. They're now all off. And now we go here and see what happens when we test. Okay. All right. Good. So here you start the unloaded latency, about the same as it should be. And now you can see it's reaching around 150, 160 megabits per second of bandwidth. And the delay, the latency is much higher because this Wi-Fi router does not have any AQM features, as it happens with many Wi-Fi routers. There are a few that do, but you can never be sure what your users will have at home. Now it's going to go uplink. Okay, and again, much higher latencies. And so not such good, great here. So now let's implement the same scenario, but with the Bequant BQN here active, with all the optimization settings, with our improved FQ codel, our TCP optimization, and our Automatic Congestion Management, ACM. Okay, we have, this is the Wi-Fi router with the 20 megahertz channel. Then we've eliminated the queues on the access router, and we have activated all the TCPO, ACM, and all the shaping features. And now we are going to see this test. Okay, mode. So unloaded latency 7 milliseconds as expected. Now it's warming up, going to 150, 160 megabits per second. Starts with high latency because ACM has to learn how to find the optimal speed that will reduce that number, latency number. While still getting appropriate good speed. Uplink latency. Similar, has to learn. And here's the end result. Much lower latency, good speeds, and A grade network instead of a C grade. So how does ACM, Automatic Congestion Management, work? It uses very advanced machine learning algorithms, which, starting from continuous measurements of speed, losses and latency for each user. It detects situations in which the user reaches a certain maximum speed and that coincides with high latency and losses. In those situations, it will try to use slightly lower speed and see if that reduces the latency and the losses, and thereby reducing the congestion. And if that works, it will start optimizing that speed limit number, trying slightly up, down to get to an optimum speed limit and with minimum losses and latency. In summary, first conclusion, AQM, Active Queue Management, from Bequant, Cambium QoE, Presim, Libre, QoS, MikroTik. It can be FQCodel, it can be Cake, variations of those. They will all significantly reduce the latency of your network when you force your rate plans. They can take a network which is not with an A grade in buffer bloat, which is not suitable maybe for low latency gaming, to an A+ network, which is suitable for all applications which significantly reduce latencies. Reducing queue size without AQM, using first in, first out queues, will only produce losses and not reduce latency. We have also seen that. AQM, whether it is Cake or FQCodel, will also produce some losses, not as many as using very small queues, but those techniques are based on preemptively dropping packets. So while they will work in reducing latency, those losses can sometimes be a problem, especially in gaming, where losing maybe 1 out of 20 packets may have implications, or in voice over IP. Only TCP optimization plus AQM as Bequant or Cambium QoE product will deliver to you will be effective in reducing latency without incurring in packet losses. And that's because in TCP, with TCP optimization, we can use the windows, the TCP window, to control the rate at which the server is sending the traffic, instead of having to drop packets to signal to that server not to send faster. Second conclusion. When speed is limited below the rate plan, which is quite typical, I imagine how many Wi-Fi routers are out there that cannot sustain the rate plans that your users may have. Or even if they can, when those are congested with a lot of traffic, or someone is lying far from the Wi-Fi router. As I say, very common situation. Only in those situations, only the Bequant Cambium QoE technology, the advanced Automatic Congestion Management and TCP optimization, the most advanced queuing technology in the market, will help you reduce latency and take a C-grade network with fairly high latency to a match an A-grade network with significantly reduced latency. So, for any more information, if you want to try this out in your network, please contact us at info@bequant.com or visit our website at www.bequant.com. Thank you.